once again, Neil Thompson.
All right, thank you very much. So, as Gil said, I'm the director of the Future Tech Research Project at MIT. And the big thing we want to think about is, what are the biggest trends happening in technology and the economics of computing that shape what's actually going to happen? Right? If we think about these very large trends like Moore's Law that have made such a big difference in actually where we end up, we want to say, well, how are these things changing? What are the other forces that are going to decide where it is that computing goes? And so that's what we're going to talk about today, and I'm going to hopefully convince you that actually in the coming decades, computer progress is going to look very different than it has in the last 40 or 50 years. And that's going to have some really important implications for how we think about what computing is going to look like, what we're going to do, and how businesses and society are going to benefit from it. So that's where we're going to go today. So in terms of the agenda, I'm going to start with the importance of computing power. I want to make this case that that's actually one of the really central ideas that we should be basing our predictions about the future around. We're then going to talk about why this is not going to look like it has in the past, why we really are at the end of something very important. And then lastly, we're going to talk about, well, where might we go after that? So I want to start with the importance of computing power, and in particular, I want to focus on an area that has been really very important, protein folding. So for those of you, this is a little bit further from computing, right? But this idea of protein folding is incredibly important because our bodies, when we produce these proteins, we produce them as a linear sequence, and they fold up into the right shape, and that determines the chemistry of how our bodies work. And so it's incredibly important for pharmaceuticals, for understanding all different parts of biology to understand how proteins fold. And for many, many years, this was something that computers were not very, very good at. And what's remarkable is in the last little while, we've done much, much better. So here what I'm showing you on the y-axis is how well we can predict, when I give you that linear sequence, how well we can predict how it's going to fold in. And on the x-axis here, we can see the amount of computing power being used. And I want you to notice that these jumps here are a factor of 10, right, for each. So these are huge differences in the amount of computing power being used. Now, what I want to show you about this graph is if you look at these systems that have done incredibly well, so, well, OK, it's not showing up here, but if you think about AlphaFold and AlphaFold 2, so these are the DeepMind systems that have done, front cover of all the major science things, right? This was enormously important that they could do so well. What I want to show you is that performance was very predictable if you think about the other people also doing work in this lab, in this field. Okay, we can show them here, right? Who were using smaller systems. And what actually happens is, if you take that kind of scaling and you go up 1,000-fold in the amount of computing being used, you see that you get this incredibly good performance, right? So I don't want to, this is in no way to diminish the achievement that what DeepMind did, right? Being able to harness this amount of computing power and use it in this clever way was incredibly important. It was an enormous achievement. But what I want to point out is that a big part of what they were doing was harnessing more computing power. And that's really important here. Let's talk about another example of this. Right? We've already mentioned this today. Generative AI, these large language models, incredibly important. Society is really grappling with what this means. It turns out in this area as well, computing power plays an incredibly central story. So this is a graph put together by one of my students and his co-authors. And what you can see here on the x-axis is we have the date, and on the y-axis here we have the training compute of AI models, not just generative AI models, all kinds of AI models over time. And what you can see is that from 1952 through to about 2010, we had this progress here, and doubling was about every 21 months, which may sound a little familiar, right? That sounds kind of like Moore's Law, right? That's because over this period, what happened is people were building AI systems, but they weren't really ramping up the amount that they were spending on these systems. They were just saying, like, I have a certain system, and then at a later point, I have a system that is more powerful, right? And I try that other system on it. And so you get this progress over time with AI really following the pace of Moore's Law. And then we have this break in around 2010. And it comes because people start to figure out how to use GPUs to do AI, and they start to get these amazing results. And people say, well, I'm willing to spend a lot more money on this. Let's see what happens when I ramp up computing even more. And we enter this second period, which is called the deep learning era on this slide, where we start doubling the amount of computing power we're using every 6 months, right? Dramatically faster than we had been before. Okay, and then we can see there's even another jump up to the red dots. So these are the large language models that we're starting to see. And now the doubling actually slows down, but you can see we're at a higher level every 10 months. So the point I want to raise with this is just that all of these advances we've seen in AI, this is not just like, oh, there's sort of a field out there that's making progress. It's a field out there that is harnessing ever more computing power to do this. And the big thing they're able to do is to harness that computing power to get ever better results. And you can look at field after field, as we have done in our lab, within AI, and you can see that this progress of how well you do is incredibly related to the amount of computing power that you're using. Okay, so that's my assertion. We don't have to just listen to just me. This is Rich Sutton at DeepMind, who said, researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run for AI is the leveraging of computation. Okay. All right, let me give you one more example of computing power before we start talking about how it's changing. And I wanted to do that because I wanted to give you an example outside of AI, but where we also see the same trend. And that is in weather prediction. So weather prediction turns out to be something that, not surprisingly, humans have been interested in for decades and decades. And we've been trying to do better and better simulations of this. And it turns out we have made remarkable progress. So now here we have on the x-axis again, we have computing power. Okay, and notice again, now we have these very big logarithmic jumps. So that's a 100-fold improvement, another 100-fold improvement. Okay, huge increases in the amount of computing power. In fact, over the timeline on this graph, there's a trillion-fold increase in the amount of computing power being used for these weather prediction models. And on the y-axis, we have the error in the prediction. So if I tell you it's going to be 20 degrees and it's actually 22 degrees, right, that's a 2-degree error. Right, so that's what we're looking at on the y-axis here. Now, my apologies to those in the room. This is in degrees Fahrenheit, because this is from the American prediction system. But what I want you to notice is just how well the amount of computing power you're using predicts how well you can do. So if we focus on this line that says day 3, which means doing a prediction 3 days out, right, we can see that these systems represented by the dots follow incredibly closely this line. Right? And this is not just sort of a historical trend. Turns out if you look at this, there are these big jumps in when people get computing and stuff. It nevertheless is incredibly predictive. Okay, so across these 3 examples, what I tried to show you is that computing power is incredibly important. Okay, these are some particularly vivid examples of it, but you can actually see it much more broadly across society. And so computing power here really, really matters. So now let's talk about where we've been getting that progress so far, and why we can't get it that way in the future. So this is, in Silicon Valley, sometimes called the most important graph ever written or ever drawn. So this is something that Ray Kurzweil put together. And what it's looking at is the calculations per second that you can get for $1,000. And on the y-axis here, you can see we have the years, and we have these different technologies that computing has gone through. And what we can see is this, actually not even exponential, super exponential increase in the amount that we can do over time. So on one hand, this is pretty amazing, right? This is just enormous orders and orders of magnitude of change that has completely transformed computing. And it's remarkable if you talk with the people who were at the early days of computing, many of the things we do today, they sort of were like, oh, I could imagine doing this. And then they did some back-of-the-envelope calculations and were like, oh, no, I don't have anywhere near the amount of computing power to do that. Never mind, right? And then decades later, we got that computing power, and they were able to do it. OK, so this seems remarkable. But I think there's a temptation to look at this and say, well, look, this is 5 technologies in these last 50 or 60 years. There's been a big increase in what we've been able to do. Like, there have been bottlenecks along the way. We've overcome them. There's this temptation to say, we're going to just be able to continue doing this. We'll just keep coming up with the new thing, right, that will allow us to continue on this trend. And what I want to point out here is that I think that that's not right, Because in these last years, the last decades where we've had these concerns about can we continue Moore's law, which is really what sort of defines the last 50 years of this, what we've seen is technical bottlenecks that we've had to overcome. But for that whole period, there actually has been a very clear path that we were going down on how we could continue to improve. And that wasn't articulated first by Gordon Moore, actually. It was articulated by Richard Feynman. So Richard Feynman gave this talk at the American Physical Society in 1959 called There's Plenty of Room at the Bottom. And it's ironic because this was just a very informal after-dinner talk, but it's probably one of the most influential talks that people have given. And this is the talk where he basically outlines nanotechnology. And if you think about that, of course, huge, huge impacts. But part of the speech is about computing specifically. And here's what he says. Why can't we make them, computers, very small? Make them of little wires and little elements. And by little, I mean little. For instance, the wires should be 10 or 100 atoms in diameter. Okay? So, that's pretty amazing that someone at this time is thinking of that. But I just want to give you a scale of what he's talking about. So if you think about the orders of magnitude in terms of what people are building in terms of transistors and switches at that era, that's like looking at something the size of the Earth and saying, you know what? I don't think the physics really changes if you take it from that size and make it smaller and smaller and smaller, all the way down to the size of a basketball. And it will still kind of work the way it is, right? This is a trillion-fold miniaturization that he's talking about. And he can see that you can do it up until you get to these 10 or 100 atoms. Okay, so that's pretty remarkable, right? That's the roadmap. That miniaturization, it turns out, is incredibly important, right? It allows us to fit more transistors on things. As things shrink, they use less power, so we can run things faster. That's really responsible for almost all of the things we call Moore's law and the gains that we've had from them. Okay, so what's the problem? Well, this is the smallest dimension of a transistor in the last while. And this is the single atom area. We are almost exactly where Feynman was like, I can see us doing it till this point, and then we have a problem, right? Then we have quantum mechanical effects, things start to jump around, all kinds of things that make this really, really hard suddenly come into play. And so what I want to point out is that this incredible vision that he had of what we could do gave us decades and decades of improvement on this very predictable, we can keep miniaturizing, and we've now hit the end of that. And that's why this isn't like other predictions about the end of Moore's law. This is one where it's not just that there are technical challenges, we don't even know what the roadmap looks like for the next coming decades. Okay, if this is true, we should see a drop in computer performance already as we start to hit these limits, and that's exactly what we see. So this is some data put together by Hennessy and Patterson at Stanford and Berkeley, and this is the year-over-year improvement that you get in computer performance on, this case is the SPEC benchmark, which is a particularly broad benchmark. And what you can see is that in the late 90s, we were improving year-on-year performance in this by 52%. A really remarkable year-over-year rate. Get into the early 2010s, we're down to 23%, and now in the late 2010s, down to 4%, and now it's be even lower than this. Okay, so this is not great. Right now, some people have tried to redefine Moore's law in terms of well, how can you do it per dollar or something like that, which is not what Gordon Moore originally said, but economists care a lot about that question, so we can look at that as well, and you see basically the same pattern. Okay, so I told you we should expect this to be different, and indeed it is different, right? We see performance improvements slowing dramatically. And that means that all of these things that we were capable of doing because we were given much more computing power suddenly become a lot harder to do. Okay, so I want to just make this very concrete. So if you think about the kind of chip we had in 1985, it would have been running at about 0.25 gigahertz. Fast forward 17 years, because of this miniaturization and Moore's law, we got a chip that was running at about 3 gigahertz. Fast forward again to today, and the most advanced chip that you could get here would run at about 5.1 gigahertz. So we got a 100-fold improvement here, more than 100-fold. Right now we're getting about 60%. That's not great. We do get 14 cores. Most people can't use 14 cores very well, but you could imagine a version of this where you say, okay, well, I got 60% more speed and 14% more cores. Maybe you got like something like a 25x improvement in your chips over these last years. What would we have gotten had Moore's law continued the way it had been? So I call this the only a dream chip. 1100 gigahertz, 1.1 terahertz, right? Your computers would be lightning fast, even on incredibly big data sets, right? You'd be able to run a lot of these big models on your own computer if you had this. This is an enormous change that we just didn't see because Moore's law didn't continue the way it was. Okay, so let's talk about the paths forward. What are we going to do next? So some co-authors and I wrote a paper about this in Science, and we said, okay, if we're not getting benefits from miniaturization, what else can we do? And we highlighted 3 particular areas. So there's software performance engineering. So this is this idea that over time, we've used this incredible abundance of computing power to make a lot of things easier for ourselves. So if you write code in Python, Python is way easier to write than C or Fortran or machine code, right? Turns out it's actually a lot slower as well for most things. And in fact, it's even funny, like you can even look at subsequent versions of Python and you see things slowing down, not speeding up, because what we cared about when we designed those is we said, we want to make it easier to program, and we have this abundance of computing power coming in from Moore's law, so we are happy to harness that. What we're going to do is we're going to start to take back some of that. We're going to try and say, well, that sort of bloat that we had in the system where we didn't care about it, we're going to try and make this as streamlined as possible. Okay, so that's one source. I'm not going to talk too much about that one today because I think we sort of have long had that ability to go between these two. What I want to talk about then is algorithms. Okay, we don't usually talk about algorithm progress, but it's actually incredibly important. And hardware architecture. So not just making these things smaller, but saying, should I design a chip differently than I have been in the past so that it's particularly good at a task? And then lastly, I will actually talk a little bit about, well, if we're getting to the end of silicon, might there still be some devices that we could do that are a little faster or have some other properties, which would also help us out? Okay, so let's talk about algorithm progress. And as I said, people don't usually think about algorithms in terms of progress, but I think it's actually very important. So here what I'm showing is 3 different algorithms over time. So I'm going to focus first of all on the red line up here, which is maximum subarray. For those of you who are interested and don't know the maximum subarray, it's this idea you have a long sequence of numbers, some positive and some negative, and you want to pick some starting place and some ending place where there's the maximum between them. And so maybe the easiest way to think about this is like if I gave you stock market returns that were up and down each day, right, and you wanted to figure out where do I buy and where do I sell to make the most money. Okay, that would be this problem. Okay, so it turns out that in 1970, there we go. In 1970, there was the first implementation of this, which was a very brute force version of this problem. And it took what computer scientists call n-cubed time, right? Which is like how many times you have to sort of look through the data in order to be able to analyze it. And what you can see is that on the y-axis here, we have the relative performance. So this is going to be, I'm going to give you the same amount of time to solve the problem as it took in 1970. And as stuff gets better, you tell me how many of these problems you can actually solve in that same amount of time. And it turns out that due to an algorithm by Grenander in 1977, we get a million-fold improvement in this. Okay? Then we get another algorithm by CMOS, another algorithm by Cadane, and we're at a trillion-fold improvement in what can be done with this algorithm. Okay? It drops from n cubed to n squared. And here we're assuming that the problem size is 1 million. Okay, so just to put that trillion-fold improvement in context, you can see this gray line. That gray line is hardware improvement. Okay, this algorithm improvement was way more important. Right? So if you were solving this particular problem, like Moore's law, yeah, that's kind of a nice side story. Algorithm improvement, really what mattered. But Notice I have another example, polynomial factorization. That's much closer to the hardware. And at the bottom one, we have self-balancing tree creation, which has had basically no progress over time. OK, so this is sort of telling you, in some cases, algorithm improvement can be way more important than hardware. In some cases, it can be way less important. Right? There's a ton of variance here, but it at least has the potential to be important. So what we did in my lab is we went and we looked at all of the major algorithm families, all the major problems that people try and solve, and the successive algorithms that people have used for them. And from this, we're able to calculate what happens to the median algorithm family. And we're going to calculate it in terms of sort of like what would be drawn as a straight line on this graph. So this is, if you think of a straight line on this exponential graph, that means sort of exponential growth over time, the constant growth rate over time. What would the growth rate have looked like over these? And so that's what I'm going to plot on the y-axis here. And so if it turns out that if your algorithm problem is small, so you're looking at, say, a list of 1,000 numbers, OK, the average year-on-year improvement for the median algorithm is 6%. OK, not great, not terrible, like something. Way better than the rest of the economy, but not great for computer science. If your problem size is 1 million, you get 15% on average year-over-year improvement. That's getting a lot better. And if your problem is 1 billion, 28% year-over-year improvement. OK, so the bigger the problem, the more benefits you get, right? If you're big tech, this is a good story for you. Let's now compare that to Moore's law. And here it really matters what you call the timing of Moore's law, right? In the 1990s, I showed you before, we were getting more than 50% improvement year over year. 2010s, not so much. Right? So these algorithmic improvements have become much more important in the story of which problems are getting accelerated and which ones aren't. OK, so that's algorithms. Let's turn now to computer hardware. So far, all of our computers have a CPU at the heart of them. And if you talk with an architect at Intel about Intel CPUs, what they'll tell you is these CPUs are a compromise. They have this list of about 200 different things that they think are really important. And they look at, when they make a change, are all 200 of these things going to get at least a little better? And hopefully, the more important ones even quite a bit better. But it's a compromise. And it turns out one of the things you can do if you're designing hardware is say, I don't want to make that compromise. I want to target just a particular thing that I care about and build a chip that's really good for that. Right? And so probably the most famous version of this is a graphics processing unit, a GPU, which NVIDIA makes. And of course, NVIDIA has done very well recently in making these things. Right? These are designed to do graphics particularly well, but it turns out that that kind of matrix multiplication is actually super useful for AI, which is why they've done so well. But that's an example of saying, I'm going to throw out that compromise and do one thing particularly well. And Google has done the same thing with their Tensor processing unit, also for AI, also trying to do better. OK, so we have this possibility of doing this. And indeed, what we see is, in the cases of AI, this has given a really big advantage. And so if you actually look at the progress on these, you can see that you get at least 35x improvement in being able to run this when you put it on a specialized chip. Hey, that's a pretty big source, right? That's not, if you compare decades of Moore's law, this is kind of small compared to that, but there's at least a possibility. So could we just continue to get better and better at building these specialized pieces of hardware? Maybe that's going to be our next area of progress. Well, the problem here is it's very hard to do for a broad range of things. And so people may be familiar with Amdahl's law, which is usually talked about in terms of parallelism, but it actually applies here as well. So I want you to imagine you have some problem, right? And almost all of it, you can say, I can do a really great job. I can put this onto a specialized processor and do really, really well with it, right? But there's some part that I maybe can't. Maybe it's the part at the beginning where I sort of divide up my work and I send it to the processors, or there's just some part of the calculation where you bring things together, right? That you can't actually take advantage of it. So what happens when you do that? Well, here's a case where we're going to build this accelerator, and the accelerator is going to speed up whatever it is we care about by some factor, right? So this is 128 times, 510, 1,000 times. So these are big jumps in how well it can do a particular thing. And on the y-axis, we have the total speed up you get assuming that, in this case, 75% of the workload is acceleratable. Right? So this is just 25%
Recording
isn't.
in progress.
So this assumes only 25%. And notice, I can give you 1,000 times speed up in what you can do, and you still overall get only a 4x improvement, right? Because that last 25% that you can't speed up is the bottleneck, and you can't do better than that. OK, well, you can say, well, but what if 90% of the workload is acceleratable? What if 95% of the workload is acceleratable? Well, look, 95, you still get a 20x accelerator wall. Right? So again, compared to what we've gotten from Moore's law, these gains are not large. So what this means is, we are going to see, I think, for sure, much, much more specialization, as we have seen with NVIDIA, as we have seen with Google, as we're now seeing with car manufacturers. But we're not going to see the decade-over-decade improvement coming from it that we saw from Moore's law. All right, my last one here today, I just want to talk about this beyond CMOS, it's often called. So beyond CMOS is this idea of, most of our transistors today are built with sort of a dominant technology. Might there be some subsequent technology which would give us some benefit? Right? Won't have the same kind of roadmap that Feynman said, but maybe we can still get some improvement. And so there's, in fact, a roadmap that the field puts together, and these are some of the technologies that they're talking about. Not really crucial for you to think about sort of the individual ones here, but I just want to pick out, my lab has done some work on thinking about these, and one of the ones that we have picked out as having the most benefit for society is this germanium silicon nanowire FETs. And what you can see here on the, which you can maybe see, in terms of the ratio relative to CMOS, so this is what's the level of improvement. If you look at the number of transistors, you can see that this is going to get us about 5 times as many transistors in terms of density. OK, again, not that big compared to Moore's law, but not bad. In terms of frequency, an improvement of 24. OK, that's substantial. That's a nice thing to get. And you can get this pretty substantial reduction in the amount of switching energy. So all of these good, but all of them still pretty small compared to what we got from Moore's law. OK. So to summarize, growth in computing power is central to the performance across many, many different areas. And harnessing it has actually been incredibly important for AI and all the progress we've seen there. But we can no longer rely on Moore's law to get these benefits. We have reached the end of this incredibly visionary prediction that Richard Feynman made, and we can already see progress slowing. So that means we have to get it somewhere else. Algorithms actually have some potential here, but it's going to be very uneven. Right? There are going to be some where you get really big gains and some where you get almost none. And that means that it's not going to be like all of computing getting better as we have had it. Right? It's going to be much more uneven. We're going to see the same thing with hardware acceleration. Right? It's not general. It does not work on it as a general purpose thing. It works really well for some things, but the more of the workload that you have that you can't accelerate, the more you're going to be very severely capped in what you can get. And then these beyond CMOS technologies, again, a nice benefit, but small compared to Moore's law. Now, you may have noticed there's a word on here that I haven't said so far in the talk, but is important. When I put in algorithms, I said including quantum. And I don't have enough time to really talk about quantum, although we do a lot of work at this in my lab. But the really crucial thing about quantum is you should not think of it as like a successor technology to Moore's law. This is not like all of computing is going to move to quantum. Only a very small number of things where there's an algorithm that quantum has access to that will actually be better. And so it's actually going to sit very much in this improved algorithm characteristic. It's just that by developing these quantum computers, we get access to some algorithms we haven't had. And if the gains we get from those algorithms are very large, then we get the algorithmic advantage that looks like the kind that I already showed you today. OK, so for all of this, what you can see is we're really entering a very, very different time in terms of computing progress. We've been at this era where we had for decades and decades this incredible improvement across almost everything. And we're now entering a world where we're going to have smaller gains, and it's going to be much more scattered. And so that's going to really change computing. It's going to look much more heterogeneous and much more like some areas improve and some areas don't. And I think that's really what we're going to be thinking about over the coming decades. Thank you.
Neil Thompson.